Thanks. I'll begin. Heavenly Father, we thank you for this day, and I just pray that you'd guide our thoughts today. Help us to glorify you again, Lord, what we do. In your name I pray, Lord Jesus. Amen. So I'm going to try to be disciplined here and just hit the high points in the connection section. I stopped believing in the projector working yesterday when I went to project the test solution for abstract, so I didn't write notes. So it demotivated me if you're writing notes. Of course, the projector's not working, so I could have written notes, but then I was like, well, what's the point of writing notes? I'm writing notes and then it won't work, and so here we are. Anyway, so we made a definition last time, which was that the connection rather the covariant derivative of y in the x direction was gamma inverse of the theta yx, right? And so in more detail, this theta yx was what? It was equal to 1/2. You do the interior product with x of the Lie derivative in the y direction of the metric g plus the exterior derivative of theta sub y. What was theta sub y? Where theta sub y is what? This is gamma, so-called gamma of y. Right. So, if you wanted to, I mean, it wouldn't be really much of an abuse. Maybe it's not an abuse at all. You could instead, you could trade out this term. I mean, what this really is then is nothing more than the exterior derivative of the metric, right, where you put y into the first entry of it and you leave the other entry open, you know? So sometimes you'll see this sort of notation in other places. That's what's going on. Because remember the gamma map. Remember what the gamma map is? It trades vector fields for forms through the metric, right? So the gamma map, I mean gamma of y, that's a one form. When it acts on x, it is equal to, oh, I think I remembered it wrong, didn't I? Is it, I can't get into trouble, right? Because the metric is symmetric, right? So, haha, I win. It doesn't matter. I'm debating whether or not the y should go in the first or the second slot. If you're working in a context with a quote-unquote metric, which was not symmetric, then you need to worry about this. Okay. In symplectic geometry, there is something that plays the role of the metric, which is not symmetric. So there is a context in which you need to worry. But hey, we're in Riemannian geometry right now, so let's be where we are, do what we're doing. Okay, so then, after much suffering, well, to me it's not suffering, but after 2 pages of gory index calculation, the following formula is derived for the covariant derivative, right? So that formula is the covariant, well, I probably better do it over here. I don't know, I wish I'd started that over foot. Make up my mind. Cameraman is complaining, let's see here. The covariant derivative of y in the x direction is equal to the sum k equals 1 to n, all right, of the sum I equals 1 to n, of course, but, and then we've got x upper I partial yk partial x lower I plus plus the sum. Sorry, it's hideous. Stink. My bad. Sum over, this is really bothering me, I and j. I'm going to get over it though. Gamma I, j, k, x upper I, y upper j. Close that parenthesis and partial k. Okay, more to the point where, so this is wonderful, right? In some sense, because now we actually have a formula we could calculate with directly, as opposed to, this is beautiful for proving identities, as he shows in nice detail in this section. He proves wonderful properties of the covariant derivative with use of this formulation, right? But when you actually go to calculate something, this is nice because it gives us a straightforward coordinate-based way to actually calculate the connection coefficients and so forth. But more to it begs the question, what's these gamma devils in the details, right? So gamma I, j, k is equal to 1/2 sum m equals 1 to n of partial g jm partial xi plus partial g im partial xj. I'm starting to really regret not writing notes. Partial g ij, it's my own stupid fault, partial xm, all contracted against the inverse metric g upper mk, and close your big parentheses. These Christoffel symbols for the Riemannian connection delta should not be confused with the somewhat related but different gamma I k comma j, all right, which he introduces on page 214, and those are just 1/2 partial g jk partial xi plus partial g ij partial xk minus partial g ik partial xj. Notice the difference. These are related but different symbols. So what's the, do you see what the difference is here? It's unfortunate that I, j, and k are used in a different sense in both of these symbols. Because I'm pretty sure you could look at this as being, this top one as being the bottom one with the j index moved upstairs in some sense. But that's confusing because there exists a j index downstairs, which is like overloading the j. If I just took this, right, and I did index right, if I raise the index j, the natural thing to do would be like sum over, let's say, m of, wait a minute. Yeah. Sum over m of g m j gamma I k comma j. To me, that would be what I would understand probably to be gamma I k m. Raising the index on the gamma, and he puts a comma to distinguish that last index from the first two. be warned, in the classical literature for differential geometry, a comma means a derivative. So, but that's not what's meant here, clearly, because this symbol, the Christoffel symbol, and that symbol, the Christoffel symbol, I mean, to be fussy, maybe you should call one that and not the other, but they're both very much related. They're both just derivatives of the metric, right? Just one has an index raised, one has it lowered. I think you can see that from the formula. All right. Corollary. The covariant derivative in the partial I direction of the partial j vector field is equal to the sum over k of gamma ij upper k partial k. Oh, he actually has this equation. I just noticed that this equation is mid page 215. But he has written it without the summation because he's using Einstein notation in this section, which means when he has a repeated index, he's writing, he's not writing a sum. It's just understood. Can you guys see why this would be true? So you have x, if x is equal to partial I, and y is equal to partial I, and x is equal to, and let me be a little bit more explicit, that means partial xi, right? And this is partial xj. Right. You got to use your imagination, but this, if we look at it, is the sum over, let's say, k, whatever index you want to use. I'll use k for the moment. But you can say delta ik, right? Delta ik, partial xi. And x, well, that is the sum over k, if you like, of delta kj, partial xj, right? So what I'm saying is the kth component of x is Kronecker delta ik. The kth component, rather of y, sorry about that, y. And good grief, the kth component of x is Kronecker delta kj, right? So when you go back to this theorem, which was theorem proposition 5.3.3 in McNerney, right?
Those sums you have for line k, should those be partial xk in both cases? Because then the complement to bring out the partial x. Otherwise it's not.
You're right. Thank you. That's supposed to be k, and that is supposed to be k. You're yes. Thank you. Very helpful. So my point is, if you identify, those are the component functions, so when you go to proposition 5.33, what happens? See what happens with that proposition? All these derivative terms are gone, because the derivative of all the component functions is just 0. So this piece is completely gone. And what do you have? You just have the last half of it, with these being Kronecker deltas, right? So you get xi is Kronecker delta kj. You get this is Kronecker delta, well, the j is used. It's unfortunate. The j is a free but arbitrary index there. It's used as a dummy index of summation over here. So we're gonna get into trouble. Maybe it's probably wise for me to actually write down what I'm saying carefully, since you guys are starting, right? So this, by proposition 5.33, I think we can all agree that the first term is gone, so we just have to worry about the second one, which I'll write sum over k, sum over, and see, this is the thing. I mustn't use I and j. I can't use I and j in the statement of the proposition now, because I and j have a fixed but different meaning already from the outset of this corollary. So I must replace I and j with something else, like p and q, or a and b, whatever you like. I'll use a and b. Gamma, ab, upper k, x, I mean, I guess I can, well, fine, x upper a, y upper b. All right, fine. And so the point is that this is Kronecker delta a j, and this is Kronecker delta b I. And so all that survives of this whole thing is what? A equals to j, b equals to I. And so we get a sum over k, right? Of gamma k I j partial k. The gamma symmetric in I and j.
Because you flipped AB to get BA.
Oh. Fair enough, I should do ji then, right? Thank you.
Oh, okay. Yeah, so you flipped the X and Y in the original.
Oh, did I?
Yeah, so up in the corollary you had.
Oh, right. I've actually, so this is wrong. Given my assignment of j and x, I have to have, and given my assignment of x and y, my stupid, I flipped, I should have did vice versa to make it match with the corollary. So as you can see, I proved the corollary for ji, I should have proved it for ij, sorry. Okay? So, so again, now I can actually, something I kind of sketched the proof of at the level of the clean coordinate-free formula, right? But now I can just prove it. So for example, if we have Rn and we have Gij equal to Kronecker delta Ij, in other words, the Euclidean n space, right? Then you can easily see that gamma ijk is equal to what? I mean, look at it. It's derivatives of the metric. If the metric is constant, the connection, the Christoffel symbols, the connection coefficients, they're 0. Right? But then what is proposition 5.3? What is proposition 5.33 reduced to? The covariant derivative xy equals to what? Sum over k of this right here, x upper I partial xi of y k partial xk, which you can rewrite as the sum over k of x acting on the kth component function of y, partial xk. That's how we calculate covariant derivatives and like just the most boring in Rn with respect to the connection which is induced from the Euclidean metric. Now, there's some more properties he points out here that I should mention to you guys. And then I'll come back and do a calculation, all right? So we have the following properties. If we have U, G, a Riemannian space, right? What's that mean? That means we have either a domain in Rn or a geometric set paired with a metric, right? Or if we're a little bit more adventurous, we could say a manifold with a metric, right? It's a Riemannian manifold. But if that's a Riemannian space with a corresponding Riemannian connection, so the connection he refers to as nabla, right? Let x and y be smooth vector fields on U. Then we have the following list of grievances. No, these are good things. These are good things. So nabla sub x, y is what? Smooth vector field. That's nice. The covariant derivative of a vector field is a vector field. That was one of the main motivating things for the construction of it. The assignment, if we take x, y, the pair, and we assign it to covariant derivative of y in the x direction, this is linear in the first argument. I'd say it's linear in x, right? But it's linear with respect to the ring of smooth functions. So you could say the module of vector fields over smooth functions. I don't know what you want to call it. It's easier for me to just say if you have f1 x1 plus f2 x2, and you take nabla of that, of y, you can pull out the f's. We can decide at a later date what that technically should be accounted as, you know. What kind of linearity is that formally? But those are smooth functions I can pull out of that entry. All right? But the second, it's also additive. I mean, well, that gives you additive. But 3, on the other hand, we have a product rule in the second argument. The second slot. Come on. So in other words, if I have the covariant derivative in the x direction of, say, a function times y, what does that give me? You can't just pull the function out. You actually have to do x acting on the function, all right, times y, plus f times the covariant derivative in the x direction of the vector field y. So you get a kind of product rule for the second slot. Okay. That was, I'm sorry, I seem to have lost my my numbering. That's actually 4. What was 3? 3 is that it's additive. It's additive in second slot. Meaning that if I had y1 plus y2, the covariant derivative of y1 plus y2 in the x direction is covariant derivative of y1 in the x direction plus covariant derivative of y2 in the x direction. So we can break up addition in the second slot, but it's the homogeneity we lose. It gets replaced with this product rule. And 5, the covariant, the Riemannian connection is in fact symmetric in the following sense. The covariant derivative in the x direction of y minus the covariant derivative in the y direction of x, all right, it is equal to the Lie derivative of x in the, well, it's this, Lie derivative of y along x. So, Sam, you're right. I mean, it would have been a misinterpretation. I mean, my calculation was wrong, but we couldn't get it wrong because, like this IJ confusion we had earlier, good news for us is that if we look at this, partial j, partial I, minus nabla partial I, partial j, well, that's the Lie derivative along partial j of partial I, right? If I did that right. Yeah. Yeah. But what is, yeah. Right. This is, but remember, this is the commutator bracket, and partial derivatives of coordinates commute.
Oh, right.
So that shows you that this implies that gamma k ij is equal to gamma k. I mean, I guess I should say ji over here. So the Christoffel symbol is symmetric in that pair of indices. And so there's a difference between this ik, this pair of indices ik here plays a different role than the j. There's a symmetry between I and k, which is not present between, say, I and j or k and j here. And if you start looking at this expression, you probably can see the ik symmetry. If you imagine switching I and k, do you get the same thing? You switch ik, this is still the same thing, and these simply trade places. So you can actually see that symmetry of the Christoffel symbols at the level of the formula in terms of the derivative of the metric.
Yeah, that's what I was thinking when I was when you first wrote that. I was thinking like a bit.
Yeah, if you can imagine yourself in the Roaring '20s, in whatever, I mean, I guess maybe, well, you guys wouldn't be drinking the moonshine, but if you could, certain people would be. And during those times, this would be the kind of notation you'd have been using for this, and this would have been the definition for the Christoffel symbols originally. Later, we come to a deeper understanding and we say these things, right? But back before we were coordinate free, we would use these as definitions, and everything would go from that point on outward. So, and also number six, the connection is compatible with the metric. Compatibility with G. This is Z of G of xy. All right, so Z acting on this function is equal to G of the covariant derivative of Z x, comma, y plus G of x, comma, covariant derivative in Z direction of y. Finally, and I think you gain a better understanding for why this is called compatibility with G as you go on and read the rest of the section for yourself and kind of absorb what he's saying and even get the rest of the chapter. The reason that that's called compatibility with G will become more clear as we go on, but I guess it's entirely obvious at the moment why that is called compatibility with G. except that it's just kind of like a natural relation that relates the vector field acting on G of a pair of vector fields to G acting on the covariant derivative.
Oh, Z is just another vector field.
Yeah, Z is just another vector field. Yeah, I know. It's Z. Z has gotten very overloaded in your other coursework, and but here it's just a vector field. Yeah, I know. Now, definition that I should make here, and this is also going to be an overloading of a term that you've already heard this semester in an entirely different context. But T of xy is nabla xy minus nabla yx, all right, minus lxy. This right here defines what's called the torsion of the connection. So the fact that the torsion is vanishing is tantamount to condition 5. All right. So for a Riemannian connection, which is induced from the metric, it's automatically torsionless. Most of the work you'll find written these days in textbooks is torsionless. It's probably an interesting and difficult question. What does it mean for the torsion to be non-trivial, and what can you do with it? I have a friend who'd like to use the torsion to somehow encode various things about mechanics. Somehow to use non-trivial torsion to control robot arms or something is roughly his idea. I don't understand, but more power to him. Yep. Yeah. Yeah. So it seems, yeah. But somehow the metric dependence here has to cancel out, yeah.
Yeah, I just wondering, what was the whole thing where derivative dependent on the dimensional ones? Like, was it?
Well, I think that's the answer to that question is more or less here. On page 220, continuing to read what he's saying, he's like, it's traditional to prove that while there are many possible affine connections defined on a domain U, so we don't know what an affine connection is, but you could study a more general concept of a connection and define something called an affine connection. Of those affine connections, the unique affine connection, which is torsion-free and compatible with the metric tensor, is the one we just built. It's this one. So this is the unique Riemannian connection that's induced from the metric G. But there is a larger world of affine connections that you can study. Yeah. But I don't think we have the technology to do that in here, nor do we want to, because that's not the point. So it's fine. All right. That's about it that I have to tell you about just general covariant derivative stuff. He has formulas for what's the covariant derivative of a one form and what's the covariant derivative of the metric itself. Oh, that's the one. Just got it. This one's actually worth doing. Example, the covariant derivative in the x direction of the metric G, if you let it act on a pair of vector fields, y and z, it is equal to through formulas in this section that I have not derived, justified, nor explained. Sorry. G of yz minus G of nabla x, y, comma z minus G of y nabla x, z, which is what? Right, it's 0 by the compatibility condition. So that's why it's called the compatibility condition. Why it's called the compatibility condition is when you sort out what the covariant derivative of the metric tensor is, with respect to, along the vector field, along x, right? It doesn't change. So that's compatibility. But anyway, he has gory formulas for taking the covariant derivative of higher tensor things in the rest of this section. I want to move along here. Now, there's two ways we could go here. I told myself I wanted to do an explicit calculation today. All right, we should be okay. We got time. So I'm going to bite the bullet, and we're actually going to try to calculate some of these things. All right? All right. I know it's kind of a mess, right? But if you can kind of take a step back and just collect your thoughts here, all I'm saying is that once you're given a metric, you can calculate the symbols. What is it?
Eat the whole apple for its bite.
Oh, okay. Okay, I'll allow it. Let's see here. So you can calculate these by taking derivatives of the appropriate metric components, and with those, you can construct these Christoffel symbols, right, by raising the index, which is simple enough. That's just, it's straightforward, but it's not that tedious. It's a pretty straightforward calculation. This is tedious. And then you take those, you put them back up in here, and that gives you the way to build the covariant derivative. All right. Now, I'm not suggesting we actually take a covariant derivative at the moment. What I'd like to do is just calculate the connection coefficients with respect to a given metric. All right. So I'm going to try to work through his example, but not in the way he does it. All right. I'm going to foolishly attempt to rework his example directly from this formula. Yeah, the Christoffel symbols. These are also called the connection coefficients sometimes. All right, let me find it. If I knew it was good for me, I would just say, you know what, let's just go on to the next section. I'll do this later. But then in my heart, I know I won't do it. So let's do it now. Let's do it now. So here's the one we want to work on. I'm going to try to do his example 5.3.6 in a slightly different way. Here we have the matrix. So this is you might recognize it. This is one of our pullback metrics. 1 plus 4u squared, 4uv. This is the pullback metric of the paraboloid. All right. Now, let me tell you, there's a reason he's doing this. At the start of this chapter, rather at the start of this section, what has he done? He has done a naive calculation to calculate the covariant derivative of a vector field along another one with respect to this the surface, which is the pullback, the surface which the metric pulls back from. All right? And so what he's doing is he's going through all this so he can reproduce that initial motivating example through the lens of this machinery. So he actually has one example he works through the whole. It's really nice what he did. I very much approve, but I'm ignoring his work and trying to do our own. Okay, so what's G? What's G upper ij while we're at it? So we got 1 over 1 plus 4u squared times 1 plus 4v squared, right? Minus 16u squared v squared. Flippity floppity. 1 plus 4v squared minus 4uv minus 4uv. 1 plus 4u squared. Does this simplify? Surely.
Yeah, that last term cancels out with one of the others.
So what does that give us?
So you have 1 plus 4u, or plus 1 plus 4v squared.
So 1 times 4 u squared plus 4v squared. I mean, this is the thing that actually puts the rubber to the road when it comes to that gamma map. Okay, so there it is. We've got that. That's done. Right? So let's, let's get to it. Let us calculate gamma. What do you want to start with? 1, 1, 1? So that would be what? 1/2? Of what? Partial. Now keep in mind these are symmetric, all right? So we don't have to, if you don't like the order that they're written, we could, without getting into trouble, we can do this, rewrite that as kj. I think I kind of like that more because then at least it matches the same pattern here, I'm going to do that. That's a small thing. So we're looking for partial g11, right? And then partial what? x1. What is x1 here? It's u. Right? So here we have x1 is u, we have x2 is v, among other things, in this example. All right, and then what? Plus partial g what? Partial g, 1, 1. Sorry, there's not a lot of contrast of, and the k, what's k?
1.
1, yeah, so u, sorry. You,
Literally partial g1, partial u.
yeah, I think I'm, okay, so yeah, this one apparently is easier than yeah, so we probably should just do 1/2 partial u of what? What's g11, is this, right? So it looked kind of terrifying at the start, but after you get done with it, it's just 1/2 of 8u, right? It's 4u. I feel better about my day. That wasn't too bad. How about gamma 1, 1, 2? So let's see here. Gotta think about it. So partial u, k is also partial u. The, let's see here, partial v on the last one. I'm just doing the derivatives to start with, then I'll think about the g's. Let's see, I'm supposed to do kj, which is 1, 2. What's 1, 2? So you guys know what I'm doing here? This is G11, G12, G21, G22, right? Just so you know. So G12 is supposed to go KJ12, which is 4UV. Poor planning on my part. Might get me in trouble. Actually, I can squeeze it in. It's going to be okay. G11? No, wait a minute. IJ. That's 1, 2 again, 4UV. And then IK is 1, 1 again, right? Which G11? G11 was 1 plus 4U squared. So what do we got? The last thing, 0. 4V, 4V, 8V, 4V. 4v. Gamma. What would be next? 1, 1, 2, 1? Sure, why not? 1/2. So partial u stuff plus partial what? Oh, v of stuff minus partial u of stuff. You know, if you notice the pattern, once you pick up the pattern, it'll speed things up a bit. This first derivative, second derivative, third derivative. See that pattern? That's how I did this. U, V, U. Now I got to think. Kj is the last two indices, which here is 2, 1. 2, 1 is 4uv. Then I'm supposed to do, the middle one is ij, which is the first and the last, which is 1, 1, which is 1 plus 4u squared. The last one is ik, which is the first two indices, which is 1, 2, which is 4uv. What's that? Yeah, the pattern, once you get into it, the pattern starts to pop out at you. No, that's a 4v. That's 0. That's a minus, a 0. 0. We like 0. Then we can do gamma 1, 2, 2. 1/2 partial u of stuff, partial v of stuff, minus partial v of stuff. I start out with kj, which is the last two, which is 2, 2. 2, 2 is 1 plus 4v squared. Then I'm supposed to do ij, which is the first and the last, which is 1, 2, which is 4uv. Then I'm supposed to do ik, which is the first two, which is 1, 2, which is 4uv. Zero, 4u, minus 4, 0 again. Ah. Now let's not be dumb about this. Do we need to calculate everything? No. This is also equal to gamma 2, 1, 1, and this is also equal to gamma 2, 1, 2. One, 2, 3, 4, 5, 6, 7, 8. Where's my 7? I'm missing the 2 2's. Okay, so gamma 2, 2, 1, 1/2 partial v stuff, partial v stuff, minus partial u stuff. Two, 2, 2, 1/2, all partial v's. This I probably shouldn't do. This will get me into trouble. Trying to do two at once. It's a surefire way to make a mistake. I'll tell you what right now. I also shouldn't say I'm going to make a mistake. That's a surefire way to make a self-fulfilling prophecy. Let's see here. It's too late. I did it. I can't undo it. What's done is done. Kj is 1, 2, 1. 2, 1 is 4uv. And then I'm supposed to do middle one, which is ij, which is the last 2, 1, 4uv. Huh, that's funny. And then ik, which is the first two, which is 2, 2, which is 1 plus 4v squared. Let's see, the 2, 2, 2. Oh, that's always going to be the 1 plus 4v squared, right? Right, the last one, it's taking these always, it's always 2, 2, 2, 2, 2, 2. It's inescapable. So what do we get? 4u, 4u, 8u, right? Oh, divide by 2 though. So 4u. And 2, 2, 2 is what? That's an 8v. That's an 8v. So it's I think it's 4v, right? Hey, that only took me 15 minutes. Hey, that's not bad. That's not bad. It's not bad. It's not bad. What's that? What's that? Ah, yeah, I was expecting more like a half hour. Now, so what if I was so foolish as to try to calculate, let's just do one of these. Suppose I wanted to calculate gamma 1, 1, 2. How would you calculate that? What's that mean? That means the sum, right, over, let's say, j equals 1 to 2 of g2j gamma 1, 1j. So that is explicitly g2, 1 gamma 1, 1, 1 plus g2, 2 gamma 1, 1, 2. Where these up here are explicitly the G11, G12, G21, G22s that we're talking about. Okay? So are these, what are these 0 or non-zero? What are these? 1, 1, 1 is, oh, it's 4u, right? So this is G21 times 4u. You write it this way, 4u, G21. What's gamma 1, 1, 2? Oh, plus 4v, G22, right? You notice we've got this pesky big old 1 plus 4u squared plus 4v squared out in front of everything, right? So I'll bring that out, and G21 is that minus, so I got a minus 4u squared v, I believe, right? And then the 2 is plus 4v times 1 plus 4u squared, I believe. That might simplify. Well, I think I got a 16 over here, though. I wanted to do that, but yeah. See, so but that does give me a. It looks like a minus, or rather, plus 12, right? Plus 12v u squared divided by 1 plus. I'm going to rewrite that as 4 times u squared plus v squared, just to confuse the students, as is my custom. And then I can factor a v out. I can factor a 4 out, 4v times 1 plus 3 u squared over, I don't know if this helps or not, I'm just fiddling. I'm not really sure I've improved. Any of the last 3 equations are about the same. I mean, whatever. Now I'm very nervous. This is a moment of truth. Or dare, I'm not sure here. If I was smart, I wouldn't look at this and just live in the world where I recalculated these correctly. All right, so, well, it's hard to judge. He has gamma 2, 1, 1. No! this 4 does not belong somehow. It was supposed to just be v. That v felt right, didn't it? Just to have 4v over the denominator. Those were supposed to cancel, which means we made a mistake somewhere. Curses. Where is it? One, 1, 2.
Okay, because you have 4u, 4u times minus 4uv. Yeah, it's correct all over there. But over here you have 4u times d21, d21 is minus 4u.
Minus 16 squared.
Yeah.
Next line.
Oh. Yay. Haha. That's my usual MO for making a mistake. I make a mistake in the line before the last. Almost without exception, that is where I make the mistake. Or I make it at the very beginning. Almost never in the middle. All right, so there, I mean, take a while, right? And this is a two-dimensional manifold.
Do we need the 4v? Do we need a 4 at that equation?
Yeah, there's a 4 there. Thank you. But anyway, I think you can see a clear path to go forward, right? Okay. Now, if you look at his example 5.38, he actually works out the covariant derivative with respect to these connection coefficients that we're calculating. And he shows that he reproduces the same covariant derivative he did at the start using his naive method and the extrinsic geometry of R3. This is all intrinsic in the following sense. Like, everything we're constructing here is built off the metric, right? Where's the metric defined? It's just defined on U. Right? So everything here is it's the geometry of the space for the space. It's an intrinsic viewpoint, right? The section starts by looking at vector fields in R3 and doing things like projecting the vector field down to the surface and so forth. That's the extrinsic viewpoint, the outside the surface viewpoint. So the goal of modern geometry, in part, is to give an intrinsic view of geometry. And so constructing the Riemannian connection is an important chapter in that story. So that brings us to section 5.4, which is, great, this is fun, but by itself, this is just vanity. Section 5.4, section 5.5 is where this comes to life. Section 5.4, we learn about, I think I can get with this. We learn about parallelism and geodesics, all right? So let me just throw out some basic ideas. If we have a curve, right? We're mostly thinking about a parametrized curve, C, all right, from I, and I'll play along and talk about Rn. All of these ideas are readily generalized to manifolds, Riemannian manifolds, without much modification, really. But suppose this is a smooth parametrized curve. A vector field along C is what? I mean, if this is the curve, here's the picture of sometimes it's called the trace of a curve. What's a vector field along a curve? It's just, you can imagine it, it's just this, right? Right? It's an attachment of a vector at each point in the curve. So he